My name's Daniel Holden. I'm a machine learning researcher at Ubisoft La Forge, which is the research lab of Ubisoft. And today I'm going to be talking to you about a new era of performance capture with machine learning. So before I tell you what that means, what the new era is, Alice, which is the performance capture department at Ubisoft Montreal, have prepared a really nice video to get you all super pumped about how performance capture is the best thing ever. So get ready. So now you're all super pumped and you've seen camels and dogs and awesome things. We're going to start with the nice, boring presentation. Okay, so what I'm going to talk to you about today, first I'm going to go through a bit of history of performance capture. Then I'm going to talk about 3 different projects which we worked at La Forge in collaboration with Alice, the performance capture department. And lots of these projects were projects which were done by my colleagues. It's not just me, it's lots of people there, and they very kindly and generously let me present them at GDC. So first let's start with a bit of history. If we look at the kind of timeline of performance capture, the very first thing that can really be called performance capture is the rotoscope. And this is extremely old, but it proved pretty effective. In particular, Disney liked to use it a lot. And the basic idea is you take a video or a photo and you trace over it, and this gives you your animation. And this was used pretty late, all the way up into the 1970s, 1980s, for even feature-length films like this Lord of the Rings film, used a lot of rotoscoping. And even past then, there were lots of different experiments using it. So, for example, in this film, there was a mix of rotoscoping and real live-action footage, and also for the obligatory Ubisoft reference, there's Prince of Persia, which used rotoscoping to get all the original animations. After this, we first start to see some sort of technology, computer-based performance capture start to be used. And there's all sorts of really interesting experiments from this time. So on the left here, you can see a system which is basically a camera which is tracking LEDs. And you can use this as a kind of very rudimentary motion capture setup by just attaching some LEDs to the character, and it will track their position through time and space. We also have here Jim Henson, who's using a kind of animatronic puppet type thing to animate a virtual Muppet, basically. So even here we're seeing some kind of mechanical motion capture being used. And then on the bottom right is a screenshot from what was at the time a CG web series called Floops, where you had these little characters which were animated by motion capture, and you had serial releases which you could follow along. So even in the 1980s, people were using performance capture for some pretty impressive things. After this, we basically start to see optical motion capture appear and start to be used. So here on the left, we've got a short clip from The Mummy, where they're using motion capture to do some of their CG characters. We also have the Star Wars prequels start to use a bit of motion capture. And at the bottom right, we have The Spirit Within, so the Final Fantasy film, which used, I think, so much motion capture they almost bankrupt themselves. So there's a lot of motion capture used here. After this, we start to see some new techniques for doing performance capture, which are really interesting. If you're from the UK, like me, and you're about my age, when you saw this video on the left, you were filled with nostalgia for Blue Peter, which was like a kids' show we had. So maybe I watched this back in the day, and this is what inspired me to do this talk without me even knowing. So optical motion capture starts to get pretty good now. And we also have some new systems as well. So on the top right, we've got basically a gyro and accelerometer-based system. And this allows you to do really cool things like jump out of a plane and get performance capture. Or on the bottom right, we have a magnetic-based system. And this one's cool because each of the markers, you don't just get the position, you get the orientation as well. So you can get really detailed capture without occlusions or anything like that. So we start to see people experimenting a bit more with what's possible for performance capture. After this, we have some new systems, and lots of these new systems are actually based on machine learning. So in the bottom right here, we have the Kinect motion capture system. And for those of you who don't know, this was actually a machine learning-based system. So they used an algorithm called a decision forest, which was very, very popular before deep learning. And it was pretty incredible that this machine learning technology was used and put into production and had this massive impact on the industry. And this really kick-started everyone's imagination for doing performance capture with machine learning. After that, we've seen lots of really awesome stuff in the last few years. So motion capture in the wild, having just a kind of video which you can take and you can get the position of hundreds of different characters in this video, or getting performance capture from video using a physically based simulation to make sure that you get some sort of accurate capture and you have a really strong idea about what makes valid motion. And that brings us to now. So now we're in 2019, and we're almost at the end of this kind of decade of machine learning-based technology. So the question is, what's happening next? So there's always a pattern between these different kind of eras of technology, which is that the previous era's technology starts to mature and starts to be used pretty seriously in production and making big, complicated things. So probably we're going to see the same thing with machine learning in the next era. That's what I imagine. Another way to look at it is a bit like this. So if we plot kind of quality against time, we can see an era as being something like this. In the beginning, some new technology comes along and it's hard to work with, and progress is quite slow. And then it reaches a kind of inflection point and we get a real boost in quality, and it starts to be used very heavily. And then we start to get kind of diminishing returns as we try and improve on this technology. And then what happens is that a new kind of style of technology comes along, and initially there's almost always a quality drop because it hasn't matured in the same way. And it's also hard to work with at the beginning, so progress is slow. But we expect that we might see the same kind of inflection point and that eventually it will surpass the technology we had before. That's one way to look at it. So with that in mind, I'm going to talk to you about 3 different projects related to performance capture. The first one is about motion capture cleaning. So the optical motion capture pipeline, it looks something like this. So the first thing that happens is we go to the motion capture studio and we run around and throw some punches. And then there's a process called tracking. And what this basically does is it takes the camera feeds, and the camera feeds are reflecting there's infrared cameras and infrared light which is reflecting the markers into the cameras. So the camera feeds, you have a kind of black and white map of where the markers are. And then you basically do some kind of triangulation to reconstruct these marker positions in 3D space. This is called tracking. And then you need to label the markers. You need to say which one of these 3D points is what. Then there's a process of cleaning where basically if any markers are occluded, you fill in the gap where they were. And if any markers have incorrect labels, you fix these labels. And then finally, there's a stage called solving, which is where you fit a character skeleton into this cloud of markers, basically. And the reason we need to do cleaning is because of things like this. So here we have an occluded marker, and here we have a marker swap. So these two markers have switched labels incorrectly, and it's completely deformed the character. So these are the sort of errors which need to be fixed in the cleaning stage. And the cleaning stage is actually quite difficult, and it's quite tedious, and it takes a long time. And this is kind of often a bottleneck in the whole pipeline. So if you want to process as much data as quickly as possible, this is often the point where things start to slow down. So what we wondered was, what if we could go directly from this unclean marker data to the character's joints? And this is a system we worked on, and we called it robust solving. And this is a machine learning talk, so we're going to use neural networks, of course. And basically the idea is that we want to train a neural network to map from these unclean marker positions to the joints of the character. And at the same time, we want to make this network robust to any errors it might see. So normally in machine learning, we need our data to be very clean, right? We want our data to be clean and nice, and in this case, we need to train it so that it's robust to unclean data and these errors. So how can we do this? How can we make sure the network is robust to these sorts of errors or noise in the markers? Well, there's one very powerful technique in machine learning to do this called denoising. And the basic idea is something like this. We take some sort of clean data. For example, here is an image of some peppers, which is fine. It's a fine image. There's nothing wrong with it. And then we artificially corrupt it. So in this case, we can add some sort of noise to this image. And then we try and train a neural network to reconstruct the original image you gave it as input. And it doesn't have to be noise in such a simple sense. It can be quite complicated. So here we can take a picture of a face and randomly crop central regions of it, and we can ask the network to fill in the gap and predict what was missing. We can also do something like take an image, remove the color, and train the network to reintroduce the color to this image. Or we can do this kind of CSI-style super resolution, take an image and down-res it, and then ask the neural network to up-res it again. And so this is a really interesting kind of general idea in machine learning, which is we can take something which is good and clean, and we can break it easily, and then we can train a neural network to do that fixing process, which is much harder. So this is exactly what we did with our animation data. So first what we did is we get a large database of skeletal animation data. And then what we do is we attach markers to this skeleton in many different random positions. So whenever the technicians place markers on the character, there's always a slight amount of variation in where they place them in the real world. So we're sort of emulating this. We're sampling some potential different locations the technician might have placed the marker. And then we attach the markers using linear blend skinning. So we just kind of virtually attach them. And then what we do is we corrupt these markers. So we have a kind of custom noise function which tries to emulate some of the sort of errors we see in motion capture. So for example, removing markers as if they were occluded, or shifting them away as if they were kind of swapped or completely different or completely in the wrong position. And then at a very high level, basically we train a neural network to map from this corrupt data back to the original clean skeleton. So going into a little bit more detail, we represent the markers of the character by taking the 3D position of all the markers and flattening it into one big vector. The joint transforms are the same. We take the joint transforms of every joint of the character, flatten it into one large vector. And we also have the local offsets. So these are the offset from the joints to the markers in local space. So this represents how exactly did the technician place the marker on the character. So we take this. And then the training algorithm looks something like this. The first thing we do is we sample a set of marker configurations. So this is this sampling of where the technicians place the markers. Then we attach them to the character using linear blend skinning. Then we corrupt them. Then we normalize this data and input it into the neural network. We denormalize, and we calculate the difference between what we got and our original input. And this is what we use to train the network. And all of this process is done on the fly during training. So the type of network we use is a feed-forward residual neural network. So I'll explain what that is in a bit. It takes as input a single pose and it outputs a single pose. So it's really working on a frame-by-frame basis. And with this network, we got more accurate results than with a normal network. So I'll explain why this might be the case. So a normal neural network, it works something like this. You have your input X, your output Y, and you have a bunch of different transformations in between, such as the linear layers or activation functions. And we kind of group these transformations into layers. So say we have several layers of the network here. And now, during training, what we do is we put our X through the network to produce a Y. We basically measure the difference, the error we got, and then we what's called backpropagate this error back through the network. So essentially, we change the weights of the final layer of the network in proportion to this difference. And at a kind of intuitive level, what happens next is that we take something like the residual of this error. We take the error which we couldn't fix by just changing the first set of weights, and we feed that back into the layer before. And so this new delta is used to update the weights before. That's an intuitive way to think about it. And this continues down the network until we get all the way back to the beginning. So the error kind of propagates in this direction down through the network. And the problem with this is this, that earlier layers of the network train slower than later layers. So the final layers, because they get the biggest deltas, the biggest errors, they train much, much faster. A residual neural network is kind of designed to fix this. So you see we have these kind of extra connections where we take some input and we basically add it to some other input. So these little nodes are like adding. And in this case, when we train it, it looks something like this. We take our X and produce our Y. We calculate our delta. And for the first layer, we use this delta to update the weights as normal. And the second layer, we use it again as normal. But after this, we're actually adding the original error we got right at the final layers. And we're using this to update the weights. And what this means is that the error gets propagated really deep into the network, and all of the layers, especially the earlier layers, train much, much faster. And the way this happens is through these extra connections. So these are usually called skip connections or something like that. And the error is basically traveling down these connections, and it's using these connections to propagate much deeper into the network. So a residual neural network, basically, the result is that earlier layers train much faster than deep layers because of these skip connections. So that's the network structure. For the training data, well, what we really need for the training data is basically a data set where we cover every single possible pose we might see the character in. We already have massive databases of motion capture at Ubisoft from all the captures that go into all the games. Even so, we wanted to find a way to kind of kickstart this process. So we captured some long takes where we tried to do exactly this, which was cover every possible pose you possibly can. So if you haven't seen someone try and do this, then brace yourself. And we did that for like 4 hours. No, not really. It was like an hour, not too bad. So in the end, we combined that with all of our big existing data set, or at least a large chunk of it. And we have about 10 gigabytes, which is about 12 hours of motion capture data. And we can train this overnight on kind of any mid-tier graphics card, so it's not a huge labor to train this sort of network. And all this sampling and corruption which we do, it's performed during training time. So every time we get a new batch of data, we do a new set of corruptions and a new set of samples. And this gives us, in a sense, a kind of almost infinite data set, at least in terms of the different errors we see. There's one more important thing, which is that you need to represent everything local to the character. And this is kind of a problem because when we have the marker data, it may already be broken. So we need to find some local reference frame, but our data is already broken. So one method we found that works fairly well in practice is to use basically rigid body fitting. So here we pick a selection of markers around the torso and a kind of reference frame, and we use this as a kind of rigid body which we fit into the marker data at runtime. And so as long as the markers around the torso are not completely broken, this process works fairly well. If the markers around the torso are completely broken or completely swapped, this is a kind of weak point in the method. So in the end, we have something like this. So we have a pipeline where we have the tracking, and we can feed the raw data into this network and get some joint transforms out of it. So here's some kind of comparisons of our results. So first here we have a comparison against some commercial software. So, I should go back. Oh, don't think it liked that. All right, bear with me. All right. So here we have what happens with commercial software. So you can see the commercial software here, it's filling in the gaps, but it doesn't handle swaps particularly well. And even when it is filling in the gaps, it's sort of filling in the marker positions in an odd way. And this is kind of a really, really tough case. So in lots of the times, commercial software does do well, but in this really tough case, it doesn't. Here's an example of our method on the same shoot. So here you can see it deals really well with this marker swap. As soon as the marker swap happens, it kind of starts to ignore this marker straight away. And here we have another example. So these are really like kind of the worst case you can get out of the Motion Capture Studio with really nasty swaps and really nasty occlusions. It's another short example. So we also wanted to stress test the method. So here the blue character here is having his markers corrupted by the same corruption function we use for training. And you can see, even though these markers are kind of going crazy and jumping around and being included like mad, the output skeleton is still pretty robust. And here we do another experiment where we basically randomly remove half of the markers, consider them occluded. And again, here it works fairly well at reconstructing a plausible pose for the character. Here's a similar one where we removed all the markers on the right of the character except for one. So he just has one marker on the hand, but he's still doing a reasonably good job of predicting what the rest of the pose should be like. So we tried to do an evaluation of this method to see how it was doing. One thing we did was we plotted the distribution of the errors. So in this plot, you can see that about 90% of the errors are less than 20 millimeters or 10 degrees. 99.9% of the errors are less than 60 millimeters or 40 degrees. And it's kind of, these numbers don't really give you a true sense of how it's behaving. So I'll show you some examples. So here's a kind of average case of our method. So if you look from a distance, you can't really tell any difference between the hand-cleaned one and our method. If you look up close, you can see there's a little bit of difference. So this is actually about 15 millimeters of difference. In this case, it doesn't matter because the pose of the character is barely affected. Here's a kind of worst case, which is also not necessarily that bad, which is if we look at the hand here, we have about 40 millimeters or 30 degrees of difference. So the character's hand is in a different pose. In this case, it's not critical. Maybe if he were holding a prop or something, it would be much worse. And here we have a worst case, which is kind of bad. So here we have about 50 millimeters of difference, and really the pose of the character is pretty different here. So in summary, we try to avoid cleaning data by making our solving method robust to errors. And one nice thing we do is this denoising, where we generate data with a custom noise function on the fly. And we trained a neural network to basically try and replace the solving task in the pipeline. So that was optical motion capture for full body animation. Now I'm going to talk a little bit about a research project we did on facial tracking. So this is a similar project, but we want to do it for faces. So for those of you who've never seen facial capture before, it basically looks something like this. So you have a headset strapped to your head and you have a camera pointed at your face, essentially. And the pipeline works something like this. So you get as input basically the video feed, which came from the camera. And then there's a process called tracking where you extract some sort of points in 3D representing key landmarks on the face. And then there's a process called retargeting where you take this 3D track data and you actually put it on the character rig, which is used for the facial animation. And there's the final stage of polishing where an animator takes the retargeted result, they take the reference video, and they try and improve the quality of the animation to add all the nuances, all the details, and give it the most expressiveness. And all these stages, other than polishing, are really kind of just things we have to do to get to where we want to be. So we'd much prefer if we could focus our time on this final stage. So one thing we wanted to look at was, is it possible to automate these stages a bit more and try and make them as automatic as possible? And so that's what we did. So I'm going to talk a bit about automatic facial tracking, which is the first stage of this pipeline. So we have many, many hours of facial animation which has already been tracked by a tracking technician or a tracking artist. This comes from all the backlog of all the production which has been done at Alice. And as well as this, we actually have a huge variety of different actors. So we have a very, very nice, diverse data set in this case. So we hope that we could learn this mapping again with machine learning in a supervised way. So what we did was we used a convolutional neural network. So at a high level, you can use this style of network to transform images into other things. So in this case, we want to transform images into a point cloud. And one way to understand how it works is that at the shallower layers, the first few layers, you have filters, and these filters are learned, and they slide over the image, and they try and extract certain features. And in the early layers, the features they extract are very simple. So it can be like edge features or points or areas which are very dark or light. And the next layer is again a convolution which learns filters. But these filters, they slide over the previous features which have been learned. So these filters learn to compose the features from the previous layer. So here, for example, you can have filters which learn to combine different edges together to make a shape, such as a circle or a corner or a square. And this basically continues down the hierarchy until the later layers combine all of these other filters and these other features to produce really high-level features, such as where the eye is in the face and these sorts of things. And then we have a series of fully connected layers, which are basically used to transform these feature maps into the 3D points, the positions of the 3D points. So we trained a neural network, we trained a CNN to do this with our data set, and the result looks something like this. So it's pretty hard to see, but the ground truth, which was done by the tracking artist, is in green, and our prediction is in red. But these points are pretty much completely on top of each other. So it was extremely accurate. And one important thing to note is that this is an actor which has been seen a lot in the training set. So this performance has never been seen before, but this actor has been seen before many times. If we tried on a new actor, which we've never trained on, then the results are much, much worse. So here we see lots of kind of jittering, and we see the points moving around and not really capturing the shape of the facial animation at all. So we can't really expect our network to generalize to situations it's not seen before. We hope that it does, but you can't always expect it to do so. So what can we do in this case? Is it simply impossible for it to work on new actors? So we tried something called data augmentation, and the basic idea is this. It's always going to be impossible to capture every possible actor in the world from all possible lighting conditions. This is just too much data. It would take too much time to acquire. So can we do something else to our data to try and increase its coverage? And this is the idea of data augmentation. So what we do is something like this. We try and use different kind of filters or effects or image processing to emulate the idea of different lighting conditions or different actors. So for example, we could have this frame here from the video, and we could add some noise to this frame, and this would kind of emulate very slightly different lighting conditions or very slightly different camera settings. We can also skew the character, so here we could try and emulate that the character's face was maybe a slightly different shape. We can also do some perspective transforms. So here we can try and pretend that the camera was placed slightly differently by the technician, oriented slightly differently. Or we can even do things like adjust the contrast. For example, here we can try and make it as if the character had darker skin, for example. And this is what it looks like when you combine all these augmentations together. So you have this original image, and you combine all of these effects in crazy different ways, and you get a kind of expanded data set in some sense. So does it actually work? Well, here is a result of our method after doing the data augmentation. So you can see that it's slightly better, but it's still far from perfect, and there's still a lot of jittering of the animation. So it seems that data augmentation, although it can improve things, is not enough to allow us to completely generalize to actors we've never seen before. But there were some kind of other interesting things. So we can try in completely different lighting conditions, completely different setups. So this is just a webcam in the office. And it works fairly well. It's not perfect by any stretch, but it produces something interesting. There are, again, some obvious limitations. So usually when we do the performance capture, we ask people to shave off their beards and take their glasses off. So if we have beards or glasses, it really doesn't work at all. So let's go back to the facial capture pipeline, and maybe we can do this instead. So maybe we can try and automate completely to the retargeting stage. So we tried to build an experiment doing this as well. The setup is pretty similar. So we use a CNN again. The only real difference is the output. Instead of outputting 3D points, what we want to output is the actual rig controls of this rig. So when we built this experiment, we got one short clip of training data where we had the rig controls and the video of the animation. And this was about 4 minutes in length. And we took the first 80% of the video for training, 10% for validation, and 10% for testing. So see if you can tell which one you think was the ground truth in this case, and which one was generated by our little experiment. So the one on the left is automatic, the one on the right is the ground truth, but I think in general it's pretty hard to tell the difference. So of course this is a very limited experiment. Again, it's an actor which we've seen, we've trained on, but it's kind of an interesting proof of concept. So in summary, it seems like CNNs are very powerful tools to apply to the facial capture pipeline, in particular if you have video. Data augmentation certainly helps generalize beyond the training set. It doesn't completely solve the problem and allow you to use completely new actors you've never seen before. And we saw some initial promise in our experiment of automating the full pipeline directly from the video to the facial rig. So it always seems interesting to try these experiments and see how far and how deep you can push into the pipeline. Okay, the final project I want to talk to you about is audio to facial animation. So this was a project which one of my colleagues very lovingly worked on, so I want to thank him again for generously allowing me to present it. So the audio to facial pipeline, at least the traditional audio facial to pipeline at Ubisoft, has looked something like this. So we have a sound of someone speaking.
The first Magi was a protector of the Pharaoh.
And then we have a semi-automatic tool which can do a phonetic transcription of this audio. So this breaks down the audio into the different phonemes. And then we have a rules-based system which can translate these phonemes into facial animation. And there's one important thing to note, which is that our pipeline for doing this, it only works in English, because the phonetic transcription tools we're using only work in English. So there's a problem when you have something like this.
Il primo Magi era chiamato a proteggere il faraone.
So the pipeline gets broken because the phonetic transcription fails. And what has happened previously in Ubisoft games is that you just play the facial animation for the English audio. And so this looks pretty jarring if you're playing in a different language, but there's not much else you can do if your tools don't support this. And there's another problem, which is how do you do the phonetic transcription for something like this? So in this case, you basically have to hand make the animation, because even if you do a phonetic transcription, the rules-based system is not going to produce something that looks very nice. So our idea, again, was what if we could try and skip this phonetic transcription stage using the data we had already? And this was a project we called Sound Matching. And the input and output looks something like this. So the input, we have our audio of our person speaking, and we extract some audio features from this audio. And these are very common features used in this sort of application. And the output is the output we got from the rules-based system. And this is important because it means the data set we trained on is English only. So we basically get our data, we try our rules-based system, and where it works, we include it in the data set. So we're training pretty much on only English audio. So again, we use a convolutional neural network for this application. And the reason is we basically have something like this. We have a time series of audio features and a time series of animation, so a time series of poses. So the input here are the audio features at each frame, and the output is the pose at every frame. So this is a kind of sequence task. And here you can employ what is a one-dimensional CNN. So here you have one-dimensional features which slide over the temporal axis. And so you stack your layers like this, and you get a mapping which maps from audio to animation. So if you do this with a normal CNN, there are some problems. So the first problem is that the output pose you get is only a function of a small window of input features. I'll explain what this means. So if we look at our diagram here, and we look at this pose here, we can try and see which neurons in the different layers contributed to computing this pose. So we can trace it back like this. We see these 3 neurons in this stage. And then if we trace it back, it looks like this, and then like this. And so we see that this pose of animation was only influenced by, around 10 or 12 frames. And at 30 frames per second, this is only half a second. It's even worse at 60 frames per second. A very, very little, a very, very small window influencing the pose. So the kind of typical way people have tried to fix this is with something called pooling. And the idea is this: you have your input, you do a convolution, and then you do a pooling, which basically reduces the temporal resolution. So you can take an average of consecutive cells, or you can also take a max of consecutive cells, but basically you're reducing the resolution on this axis. And then you do convolution again, you do pooling again, and you end up with something like this. And now if we trace back the influence, we can see that a single frame of animation is influenced by almost all of the audio input. The only problem is that our temporal resolution on our output is extremely small. So here our input was at 30 frames per second, let's say, but our output, we only have 4 frames to cover the same amount of time. So we're losing a lot of resolution, which means it's either going to look jerky or it's going to be way too smooth. So With pooling, the problem is that the output is low resolution and the high resolution details are not preserved. So this is where an architecture called the UNet comes in. So the basic idea here is that we do convolutions and we do pooling and convolutions and pooling, and then we do upsampling. So we take our produced output and we upsample it again. So you can use bilinear upsampling or nearest neighbor, whatever you want. And then you concatenate the features from the corresponding layer, which is the same size. And so you concatenate these neurons together, and then you keep doing this, and it looks something like this. And you can see now that the output animation is high resolution again. It's the same resolution as our input, and so we haven't lost any temporal details. And we can also trace our influence again. So here, if we trace our influence down like this, we can see that this output frame is still influenced by a huge amount of the input. Or you can go via these skip connections, these concatenations, and you can see that high resolution details also have an influence on the output frame. So you end up with an architecture which has a large receptive field, but also very high details. Yeah, so that's what the UNet does. There's some other kind of interesting tricks you can do, which really help a lot. So one is to augment your data set with sped up and slowed down versions of the data. So this works really well for languages where people speak very fast, like Portuguese and Japanese. And you can also post-process the output with some sort of smoothing or sharpening filters. And this gives the animators a little bit more control over what it's finally producing in the end. So this was a really, really interesting and really successful project. And it actually shipped in Odyssey and was used to generate all of the facial animation for all of the languages except English. So I've got a short video here.
Você queria conselhos da Oráculo?
Dela? Não, porra. O ar da minha bunda daria conselhos melhores.
E por que a procurou?
Fizemos um acordo. Acho que não faz mal te contar. Ela me diz de onde os peregrinos estão vindo. Então eu faço o transporte para a jornada deles e eu e ela dividimos o ganho.
Então você está me dizendo que a Oráculo tem intuição divina sobre de onde os peregrinos virão?
Porra, nunca! Ela pergunta aos fiéis sobre a movimentação nos portos e depois me fala. Só.
Cassandra, sei tu!
Febe,
Avevi promesso che ti avrei rivisto ed eccoti qua!
Ti avevo anche detto di stare lontana dai guai.
L'ho fatto! Beh, ci ho provato.
Come hai fatto ad arrivare qui, Febe?
Beh, ho fatto un po' di dracme lavorando per Marco.
Hai pagato qualcuno perché ti portassi ad Atene.
So, it seems CNNs are a very powerful tool for dealing with parts of any capture pipeline which has time series data. In particular, UNets are very powerful for these sequence-to-sequence tasks because they can preserve resolution while also having a very large receptive field. And one thing that I think is really important is we can get training data using our existing pipelines. So in this case, all the training data came from the existing pipeline for English facial animation. And because the movement of your face and the sound you produce are strongly correlated no matter what language you're speaking, this proved a really powerful data set, even if we want to apply it to different languages or shouts or screams or grunts and this sort of thing. So I think it's really interesting if you can find creative ways to leverage your existing pipelines and get your own data sets. Okay, so the future. So the map in Odyssey was 130 squared kilometers, which is absolutely ginormous. And it's clear that if we have these big worlds and we want more content and we want richer content, not all of this can be created by hand by artists and designers. It's simply impossible to fill this world with this much content. And I think there are many ways to tackle this. There's procedural generation techniques, there's data pipelines and efficiency. But one interesting thing which puts performance capture slightly different is that it's more about kind of enabling artists and animators to almost direct and curate. So they can go to the real world, they can find things which they like, and they can then go and put them in the virtual world without too much trouble. That's the idea. And I think that's a really, really powerful tool because it allows them to not build everything by hand, but instead they can kind of allow their creative vision to be much more natural. So another thing which is really important to say is that there's still a huge way to go to making this tech practical and stable. So if you remember the video I showed at the beginning, there was camels and props and dogs and one-off captures and all of this sorts of really complicated things. And taking these new approaches and scaling them up to this level is going to be a massive challenge. So it's not like this tech is already ready to solve all your problems, but it's starting to get there and it's starting to ramp up. The second thing is that no system can survive as a black box for long. So it's really important that engineers and technicians who are dealing with these systems have at least a high-level understanding of how they work and what the differences are between data-driven systems and more conventional systems. So this is a huge change, especially for people who have spent the last 10 years in optical motion capture riding that curve and making these small refinements and getting huge amounts of expertise in this particular field. This is a massive change, but it's really, really important. And finally, I think there will always be a need to refine the output of these systems. So if you build a system which is a black box and where the output can't be adjusted or controlled, it's almost a certain that it will fail in some way. So we always need some control, whether the control is on editing the output or actually tweaking the parameters of the system. This is always going to be required. So I would tell you to go to this talk, but it already happened. So you'll have to see it on the GDC Vault. But Stephen Shaw, who I worked with on these research projects, has a really fantastic talk about all of the practical implications of industrializing this sort of tech. So if you're interested in the story of what happens when you try to industrialize this tech, what sort of things you might encounter, I think this is a really fantastic talk, so go and check it out. So in conclusion, according to my timeline at least, the era of machine learning is almost over. And what this means is that you're going to start seeing the tech in your pipelines, so start getting prepared. So thank you very much. Yep.
I have a question about your choice of models. So you mentioned you're using CNN for the sequence-to-sequence task, but I think it's kind of natural to use recursive structured model. Have you tried that? And if you have tried, what made you decide to use CNN structured instead?
Yeah, it's a good question. So recurrent models like RNNs and LSTMs, I think they're good, but they're much more effective, in my experience, where you need online prediction. So if you have a offline setup, I really like the CNN and the UNet structure. One reason is that it's much, much faster to train. Another reason is that it's much less complex, and you can really have an idea of, say, how big your receptive field is, what your filters are learning, this sort of thing.
Okay, so you think it's more about model tuning? So
actually, I think the reality is that both models will work pretty well. The much more important thing is your data set and things like the denoising technique I presented. These are much more important than your exact model.
Okay, then how did you collect the joins, I mean the ground truth for the performance capturing part? The
Yeah.
joints, yeah.
So the ground truth comes from our existing database of animation, which we've captured through the years at Ubisoft.
Thank you. Thanks for talk.
Hey, that was a great talk.
Right.
For the sound matching project, when you switched to the UNet, did you find that it also introduced kind of like global uncertainties when there was like a local uncertainty would then cause kind of like global
Yeah.
problems?
Yeah, so the difficulty is if you have some sort of ambiguity. For example, if the person makes a very similar sound but makes a different facial movement, that can happen. That can end up kind of blurring your results. And if you have a larger receptive field, that can often happen more often. So I found that, we found that sometimes the sharpness can go down a bit if you have a very large receptive field. And you have to choose your sizes of everything quite carefully if you want really nice results.
Thanks. Ed, one other quick question. Was the English version of that system not used because the procedural rule-based system was still working better?
There were a couple of reasons. One is that the English is usually a little bit more polished and adjusted by animators in the final product, because obviously this is played a lot in English.
Thanks.
Hi, thanks for your talk. The first question is about the speech features. The user features is the MFCC.
Yeah.
But to the best of my knowledge, the MFCC depends on the human. For example, my voice and your voice, between these two voices, even when we speak with the same content, the same utterance, but the features are different.
Yeah.
How do you think about the model, CNN models? Is it sensible to the difference of the speech features?
Yeah, so you can do some things like pitch normalization, which removes a little bit of the variance. But we also have a very large database with many different speakers, and I think this helps a lot.
Okay, and the second question is about the multimodality of the movement. I observe the demo video. The movement, I can observe the lip, mouth, the eye gaze, eyelid, and eyebrow, and head, and the body movement also. My question is, which parts, which modalities of the movement are synthesized by the deep learning models?
Yeah, it's just the lip movement. So there was
just
a really,
the lip.
Yeah, there was a really fantastic talk yesterday morning about procedural cinematics in Assassin. So you can check that talk out. They spoke a lot about the other things which are generated, such as the gestures and the lookouts and everything like that.
Thank you. I come from NetEase China. I have been working on the same topic with you. Thanks.
Thank you.
Hey, thanks for the talk. It was really informative. I just had a question about data augmentation whenever you're adding different kinds of noise in and how you determine, you said you use noise, skew, contrast, difference, how you determine which kinds of noise to add in and which are most effective and how much to bias toward those whenever you're adding that kind of noise.
Yeah, I think it takes a bit of kind of intuition to do this, and we experimented a fair amount with different which filters you apply, this sort of thing. But in the end, we didn't really see much of a measurable difference. For example, there was no filter we added which suddenly made everything work perfectly. Just noise is useful. Things like the translation and skew and scaling are useful. All the kind of more advanced filters beyond that, well, it's hard to tell.
Cool, thanks.
Hi, thanks for the talk, first of all. My question is, if most of the errors in the pipeline are introduced by optical occlusion, why have other hardware solutions like magnetic mocap tracking fallen out of use in favor of optical?
Yeah, it's a very good question. So there are some really fantastic advantages to optical motion capture. One is that the accuracy is extremely high, sub-millimeter in many cases. Another is that it's very, very simple to put a suit on and to get going. And it's also very simple to, say, put a new prop together, put some markers on the new prop, do these sorts of one-off captures. It's not I'm not the guy who evaluates all the different motion capture systems, but at least in my personal experience, I found lots of the other systems, they can struggle to get exactly the same accuracy and flexibility you get from optical motion capture.
Okay, thanks.
Hey, Daniel. I have a clarification question on the first part of the talk. Just in the architecture, I believe that when you say dense, you mean fully connected, not as in dense nets, right? Because you weren't using convolutions in that case.
Yeah, that's right, fully connected.
Yeah.
Oh, hi, I just wanted to ask about something from the Stephen Shaw talk the other day. He mentioned one of the challenges has been footfalls, and I was wondering, how do you address improving that with the strategy?
So when we went to industrialize this, what we did was that we built a system where our result would only try and correct the system if it had some confidence that it was wrong. Otherwise, it would leave the markers as they were. And in this case, for example, if you have a footfall and there's very little difference between what our neural network is predicting and what we saw, then we leave this foot alone and we keep the original data. And this keeps the feet extremely accurate. So yeah, there's more details in Stephen's talk about this sort of thing.
Thanks.
Thank you. Okay, thank you very much.